Hey everyone, Christian is back with another webinar on catalyst manufacture today. And as always, I represent Hulteberg Chemistry and Engineering. We specialize in heterogeneous catalysis, working all the way from research development through upscaling into production of catalyst materials. And we can help you anywhere from idea to implementation. Today, I will try to open up the blackest of the black boxes in catalysis. So catalyst manufacturing. This is something that large industrial companies do and do not talk very much about. So the outline of the talk today is a short introduction. Then we will go through the manufacturing of both bulk catalysts as well as impregnation of pre-shaped bodies. And then there will be some conclusions. It's about 30 minutes in time, so a little shorter than previous webinars. And as always, there are handouts available in the client for you to download, or you will get the same with an email sent out to you after the fact. All right, introduction. So, as I said, this is an area with quite some mystique. So it's very little published in this field, and it has to do with the fact that this is much less relevant with respect to research, and it is rather intense industrial activity. But there is, in general, two types of catalysts. We differentiate bulk catalysts. Bulk catalysts are used in ammonia synthesis, hydrocracking, also for zeolites, or zeolites is categorized into this category. And then we have the other category, which is impregnated catalysts, which are your typical precious metal-based catalysts, but also VOC abatement catalysts that are base metal based. We can break it down. So we have our bulk catalysts here on the left, and typical catalysts include precipitations of silica alumina. So you make a gel, you form a precipitate. Silica alumina type catalysts can be hydrolysis of carbonyl sulfide, for instance, those type of catalysts. You can also make them via hydrothermal synthesis. And this is how we make the zeolites, or indeed through fusion or alloy leaching, like the Raney nickel type catalysts. Bulk catalysts is when the entire catalyst consists of the same material. And this is unlike the impregnated catalysts, which has one support material, and then the active phase is spread out all over the surface of the surface enhancement material. Typical methods for preparation is wet impregnation. It's done for automotive catalysis. Incipient wetness, platinum on tin on alumina, for instance. And then impregnation is also ion exchanging in acidic zeolites. But let's start to go through the bulk catalyst. The preparation of these starts from the metal salts. So we make them by making a catalyst that is made entirely from the active material. And this implies that the cost of the material has to be rather low. Otherwise, this is a too costly approach, because if you have an expensive active phase, you really want it to be in contact with your gas phase and maximize that contact, which you will not do in a bulk catalyst. And irrespective if it's a bulk or an impregnated catalyst, the preparation is a multi-step process, and it can be easily broken down into these steps. First, we make the actual catalyst. So here we take and we mix salts, and we stir and we change pH, and we form either a precipitation or a gel. Then we take this and we send it to some kind of post-treatment. It's usually filtration, drying, and calcination. And then we end up with a finished powder, but that powder can't be used in an industrial type reactor. So we go into a forming unit operation. Forming is normally extrusion, tableting, or granulation. There are other methods too, but those are the most common ones. And finally, we might go into or need an activation step for the catalyst to be transferred into the active state. The precipitation, gelation, is the first thing that happens. So we take and we mix the metal salts that we need, the alumina, silica, and whatnot, and we mix it in the desired stoichiometry or molecular ratio. Then we change the pH, and that makes the salts lower in solubility, and there is a precipitate. So we can dissolve nitrate salts, we change pH, and then we form a gel solution, precipitate, forming a gel. The equipment for doing this is rather straightforward. We use stir tanks, so stir tanks that are heated and potentially also cooled to maintain a good operating condition. A normal operating condition is roughly ambient up towards 60 degrees C. The most common tank material is stainless steel, but there is a severe risk of corrosion products, and that is not to mainly that it damages the tank itself. It's that the corrosion products will contaminate the catalyst. Iron or whatever, nickel is in the steel, will end up in the catalyst preparation and act as a catalyst poison. And since catalysts are normally produced as a sort of a fine chemical, the plants are normally multi-purpose production plants where there are several products produced in the same equipment. So cleaning and process hygiene is, of course, a very important aspect of quality control. Then one thing that shouldn't be underestimated is the time needed for precipitation, because there may actually be an idea or a need for aging of the precipitate. And this is when you first have changed your pH, you get small particles or floccules that form, but by allowing for these to settle and combine over time, we can actually end up with larger agglomerates of this initial first particles. And this is then easier to separate, first of all, so larger particles are easier to filter, but it's also impacting the final catalyst porosity. So we need to take care of this step, and we need to make sure that it's always the same. And it also moves us to the next thing. That is that we need to transfer this slurry from the tank to wherever it's further upgraded. And when we move it, we want to avoid as much as possible to do high shear pumping, for instance. So gravity is a preferred method, just allowing it to pour out with using gravity as the driving force, because when you do pumping, you might actually disrupt this aged precipitates and break them up, and we don't want that. Then the next step in this production chain would be some kind of filtration, so separate the catalyst from the liquor or whatever you want to call it, the residual water that is left after the preparation. This is actually quite difficult, and the reason why is because when we want to create high surface area catalysts, we need to be quite close or actually form a gel. And this gel is, of course, much more difficult to filter, and it takes a very long time. So when we do this filtration, the control of temperature and the control of pH are very important parameters. But in general, when we have these slurries and these gels, we use rather ordinary filter techniques. And it's actually quite straightforward type of equipment. So you have your plate and frame filter, you have your rotary vacuum filters, but also line and disc filters. You can also do centrifugation, but we normally try to avoid this because, again, the shear forces are too high in this case for most applications, but I'm sure that there are some cases where it does work. And so you have to assess that from a case-to-case basis. Next thing is to take the filter cake. So we end up with less wet material, and we need to remove the water from it. So the thing that we do is drying, of course. So the heat that we supply for the drying can be either electric, that's what we use, or it can be from the combustion of a fuel, normally natural gas. And here, if you do use natural gas to dry your material, it's actually important to make sure that you have no, not direct firing, so that there's no direct interaction between the material, the catalyst, and the flue gases from the combustion, because otherwise there might be CO, there might be small amounts of sulfur. The odorant in the natural gas may form sulfur components that will end up in your catalyst and potentially deactivate it. Another thing that you need to take care of is, again, coming back to the producing several different types of catalysts in the same equipment. When you have these recirculating drying ovens, there might be a risk that you have catalyst particle transfer from one batch to another, and the first catalyst might actually be either deactivating or impacting the performance of the next catalyst. Say, for instance, that you want to do selective hydration, and you're a silica based catalyst, and mixing it with some alumina which has acidic sites might actually change your selectivity, so that you get problem with dehydration instead of hydrogenation, or losing selectivity basically by having material carryover from one batch to another. But for the drying, it's actually standard dryers, tunnel dryers, drum dryers, or flash dryers, but also spray dryers. And spray dryers is sort of a beast on its own. This is nothing that I have practical experience with myself, but I have a lot of respect for doing this. And basically what you do is you have your material sprayed into a large void here. You have it in contact with preheated air, and the catalyst material is then dried on the way down, and you separate it here in a cyclone. And it's used for fluidized catalysts or any other catalyst where you have small particles, but it's also really, really good for handling these gels. So if you have a case where you form a rather severe gel where filtering is rather challenging or even impossible, then going to a spray dryer is a good alternative. But as one person in the industry told me, that when you find someone who can operate a spray dryer, you never fire him. So you have to have respect for the difficulty of operating this type of equipment from a practical standpoint. Next thing that we have to do is calcination. Calcination is the heat treatment of the catalyst, and we see not only heat treatment but also a transformation of state. What final temperature you use depends strongly on material and application, but normally ranging from 500 to 1,000 degrees is quite normal. But of course you have outliers in the high end, 1,400 degrees for making alpha alumina. You have outliers in the other end, like ruthenium and copper, which want or need lower calcination temperatures to remain some of the surface. But the key thing in calcination is that you have this transformation of state, that you start, for instance, with a nitrate and you form an oxide, or you start with a boehmite, which is an alumina species with hydroxide, and you form another phase. So the boehmite hydroxide goes into a gamma alumina, for instance, which is the one of the crystal forms of aluminium oxide. But the calcining, there's also a large influence of the atmosphere. You see having a gas flow, for instance air, flowing through the catalyst is really common, and it not only improves your transfer of the heat from the gas to the catalyst, but it also influences the calcination environment. So, and for that reason, there might also be recirculation, and recirculation is not only for recovering the heat, but if you, for instance, have high concentrations of NOx built up in the system, the NOx slowdown might, or NOx buildup in the system might actually slow down the decomposition process, and that might actually yield smaller particles. And now we're talking supported metal catalyst, but there are these influences of the calcination environment. And calcination can be either batch-wise or continuous. We mainly do batch-wise calcination, which put rather high requirements on our gas purification systems, which basically you reach a temperature, for instance, it's a rather discrete temperature where all of your NOx is transferred, or all of your nitrates is transferred into NOx at the same time, and you need to handle this large emission in a short period of time. For continuous systems like belt furnaces and rotary kilns, you can actually have a more continuous flow of the NOx coming out of the system, and perhaps also better temperature control. The good thing is that these calcination procedures are normally or almost always endothermal. So if something happens, you lose power, it will all just die out on its own. All right, so we've now made a calcined catalyst, but one problem when we end up with the calcined material is that you might actually have foreign ions trapped inside this powder. So when we do the precipitate, if there are contaminants to the starting material, starting chemicals, these will end up entrapped inside the gel or the precipitate, and those foreign ions can be like sodium, it can be other alkaline, but it can also be anionic compounds like chlorines or sulfates, and they will be really firmly boxed in on this gelling. And it's really difficult to wash them out from the precipitate, and therefore it's actually quite common to do a rewashing after the calcination to remove these ions. And to facilitate the removal, we actually also employ ammonium carbonate, which is nice in that it has both anionic and cationic activity, so it can exchange for the carbonate group for the sulfate group, for instance, and we can then dry it again, and when we calcine it or dry it at high temperature, the ammonium carbonates will decompose into ammonia and CO2 and just leave a clean surface after it. So by using something to clean it with, we can improve purity further. All right, but now what we have is a powder that is clean and it's hopefully catalytically active, but that doesn't help because we can't use a powder in an industrial type reactor because it creates too much pressure drop. So the next thing we need to do is some kind of forming operation. And forming is required for non-fluidized catalysts. We usually do some kind of pre-densification. So you need the catalyst, you mix it with water and some binding agent, and you form a paste or a dough, and you treat it to make sure that it's well mixed. This can also be combined. So if you look at this washing ion exchange step that we just talked about, we can actually combine them and do them. And we can also, in this step, add both tableting aids or binders, as I mentioned, depending on what forming method we want to use. And then for forming, we actually use a few different methods. Tableting is a very good way of achieving hard, well densified powders or tablets, and you can use them where a large amount of mass is important in the reactor. So any equilibrium reaction like the water gas shift or the ammonia or methanol synthesis, tablets are great because you get a lot of mass into the reactor. It's basically limited by the actual reaction on the surface and not transport limited. Another very common way of doing this is extrusion, where you take this paste and you push it through a die and you get smaller extrudates out of that. They're round and elongated. Or if shape isn't that specific, you can actually do something called granulation, where you form round-ish type catalyst particles, but you get a distribution in size and it's less precise than if you do round tablets, for instance. The bulk catalyst, the formed tablets and extrudates and granules will have a lower activity compared to the powder. And this is because the forming of these material will introduce diffusion limitations. And we might also need to add different aids like graphite, silicates, or magnesia talc to help us in the forming, especially for tableting. The dyes that we're using are quite sensitive to mechanical wear, so adding graphite will help us as a lubricant, more or less. The graphite is removed afterwards by heat treatment, but the silicates and the magnesia will actually stay. For tableting, we actually first screen the powder that we have produced, and it depends on the size of your tablets. Then you need different screens to make sure that there are not any large lumps left. We add this spilling aid, the graphite or whatever, and the graphite, as I said, might require this post-calcination. And for doing the breaking up of the powder, we might actually have to do a grinding, and that can be done, for instance, in a ball mill. Ball mills can also be used for wet grinding, where you add water and a powder, as well as either, well, most likely you use alpha alumina balls for making sure that you get a smaller particle fraction and a well-dispersed material slurry. For the tableting, you take the ground and sieve powder and you add it. So we have a feeder here which feeds in our catalyst powder. We scrape it off to make sure that it's the same amount in each tablet. We then have an upper and a lower press or punch, and we first start with a pre-compression, making sure that the tablets are pre-densified, and then we apply more pressure over here in the main compression roll, and we end up with a small tablet which is then ejected and sent out of the machine into a storage area. And this is, of course, exactly what you do for making any other tablets, if it's pharmaceuticals or whatever. The difference is that you can make much larger amounts of tablets than for pharmaceuticals. For instance, the market cap is bigger, so there are also other hygiene requirements in this, of course. It's more chemical safety than hygiene for the tablets. Extrusion, it's normally combined with the densification. So we form this moist clay of catalyst powder. We add it with a binder, and we also try to push it through a die, and these dies can be basically any form, and you use normally in industry round or tri-lobe, quadrilobe shapes, and the lobing is on the side, so it creates a little larger surface area, but it also contributes to lowering the pressure drop of the system. And it is also possible basically to do any other shape that you want, but the limit is roughly 20 millimeters in diameter. These clays that we create are rather thick, and you have to apply a really high pressure behind the die to push them through. That leads to, so there's actually a rather large expansion out of the die, so the die holes are significantly smaller than the final size of the extrudate. Then what you do is you, again, take these extrudates, you dry them, you calcine them, and you post-treatment, and it can look something like this, where you push with force through a disc and you form these like spaghetti-like clay catalyst material. You put these in a dryer, and then you actually break them up in some kind of grinder, and then you sieve them to make sure that too long and too small particles are gotten rid of, and then you use the final material in calcination for stabilizing the material in the final shape. But you can also do other extruded shapes. So here we have a Denox catalyst that is extruded, and you can form it into different types of shapes, different type of monoliths. And the key here is that the entire monolith is made up of the same catalyst material, and you extrude it. Then you have a metal wire here for cutting, so you lower this down and you cut them into standardized sizes, normally 150 millimeter long. Finally, granulation is taking your slurry, and you have a rather thick slurry, and you spray it onto a tilted disc which is rotating. This rotation makes the spheres build up, and when you have different particles mixing and you stir it, you will actually see a concentration of the larger particles at the top. And you can try this at home with sugar or whatever you want, and you can see that the larger lumps will actually end up on top when you shake it. And since we have an angle on the pan, the largest particles will actually fall out of the pan and into a storage unit. And depending on the tilt of the pan, you can actually control your particle size, but of course it also depends on the slurry quality and all that. So we do form round-ish material, but it's much less uniform than tableting, but as a low-cost alternative, it's actually quite attractive. And again, once we've done the granulation, there will be some kind of post-treatment like calcination and activation, drying. And this is an example of a pan. So basically, depending on the tilt, you will see accumulation of the material down here. The largest particle will be on top, and they will fall out of the pan. All right, so that was bulk catalyst. Let's now talk about pre-shaped bodies. We call it pre-shaped bodies when the support material, for instance, aluminum oxide, in this case it's delta alumina, which has been extruded and it comes to us or to anyone else, and we add an active phase for transferring it in from a support into a catalyst. But pre-shaped bodies can also be other forms like ring shapes or monoliths. And again, we need to go through the unit operations of making these pre-shaped bodies. And we again have to make the catalyst or the support. So we start by preparing the support, and it's done just as before. With precipitation or gelation, we do the same post-treatment, filtering, drying, and calcination, and we need to do forming, so extrusion either into tablets or extrudates. We would normally not do monoliths at this stage because monoliths are done differently when we want to use them for pre-shaped body impregnation. Then we have this extra stage here where we actually add the active phase, and it's done either with impregnation or with ion exchange. And again, we need a second step, which is drying and calcination within the post-treatment. But here we already have the form that we decided upon in forming the support, and we can then go on and do some kind of activation, either in the catalyst factory or indeed in the plant where it's supposed to be used. With pre-shaped bodies, there is two types of treatments to be considered. So it's either wash coating of monoliths, and monoliths are normally supplied either as ceramic monoliths, and they're usually cordierite or mollite, which is different blends of silica alumina oxide. Then we wash coat these. So we prepare a slurry of, for instance, aluminum oxide mixed with water and other things. We do a wet milling of this powder, and we mix in different additives like, well, ethanol and nitrates to make sure that we get the right rheology. But we also have to have a binding agent. Binding agent can be boehmite, like the aluminum oxide hydroxide that transforms into gamma alumina, or it can be water glass or something that makes it stick to the material, or a polymer, something that just makes it, or glue, polymer glue, that makes it stick to the monolith. The impregnation of the active phase on the support can be done either by incipient wetness or wet impregnation. And this wash coating of the monolith can be done on different types of carriers. Either they're metal monoliths, where it's really important that you do a suitable pre-treatment of the metal to make sure that the wash coat can stay on the metal. It's done on cordierite monoliths, which are simpler because there's porosity in those. And then you have foams, ceramic and metallic foams, which are interesting from a performance perspective because you're actually combining the pellets and structured bed. So you get the benefits of having high mass and heat transfer, as well as the rather relatively low pressure drop of a structured bed. Slurry can be applied either by dip coating or pump through, depends on your preference. Then excess slurry is removed either by pressurized air or indeed vacuum. So you can actually get the excess slurry out of the system by blowing it out or sucking it out. And that's how you make your monolith. Then the wash coats to stick on needs to be dried and heat treated. So again, you do drying and calcination to make sure that your support material sticks to the carrier, the monolith. Final thing incipient, so the impregnation of these pre-shaped bodies. And you can do either incipient wetness, which is a rather straightforward method where you basically measure the catalyst pore volume. You prepare a solution of the chemical salt. Say you want to add platinum to the catalyst. You blend, you know the catalyst pore volume, you know that you have 1 kilogram of catalyst, and that has a certain porosity, and it can suck up a certain amount of water, and you want 5% of platinum. Then you prepare a mixture which contains 5% equivalent with the water that is suitable for the pore volume. You then take this liquid and you pour it over the catalyst support, and it's perfectly sucked into the catalyst, and it's still actually dry to the touch. So it's inside, but it should be just inside and not overflowing, but not too little. Then what you need to do is again drying and calcination, and normally this yields a rather even distribution of material. So if you have a pellet, you will have normally the platinum in this case, for instance, distributed rather well inside the body. But you can influence this distribution rather drastically with the drying temperature. So by drying at higher temperature, you will actually see an accumulation of the active phase in pore mouths of the system where the majority of the evaporation happens. So you can control the distribution of the material, but it's more difficult than with wet impregnation. And wet impregnation is where you have a large excess of the active phase solution. So you have a large liquid volume, and you take a small volume of solids, and you put all of these solids inside the active phase solution. And then there's a low concentration of platinum, for instance, in this case, that is floating around in this large amount of liquid, and it absorbs. So there's a chemical interaction between the ions in the solution and the material of the pre-shaped body, and you allow it to equilibrate, and you will find that the platinum or whatever ends up on the material, and you remove it from the liquid, you dry the material and you calcine it, and then you have to add some makeup platinum for the next batch that go in there. And then you can actually do really nice things. You can vary the distribution of the material depending on the pH of the solution, and you can then prepare, or you can control how strong the adsorption will be, because if you have a very strong adsorption, you will only have a thin layer of adsorption, and you can do all different sorts of tricks to also control it in other ways. So then you can end up with homogeneous distribution. You can also create an eggshell where you concentrate it to the outer surface, and then you can do an egg white distribution where you first add something which has a very strong adsorption, and then you add the actual platinum or whatever you want the active phase to be to the catalyst particle, or you immerse the catalyst particle in that solution, and it will find its way in, and it can't absorb where the very strong material is absorbed, and then you end up with this egg white distribution, or indeed this egg yolk type distribution. So to conclude, this is to a large extent experience-based, and there are really many steps involved in forming a catalyst. They are both chemical, but they're also thermal and mechanical. And since these recipes are trade secrets, it's really difficult to find them online, or actually anywhere in written literature. And the final recipe also includes the main chemicals, but also like structural promoters and conditions for processing steps. There are a few things that you can read. They're listed here. I've seen that I've received quite a few questions, so I will answer them in an email sent out afterwards. And with that, I would just like to thank you very much for your attention, and I wish you a very nice day. Thank you.